Hello, everyone. Hello there, and welcome to a new ceremony for our Masterclass students' final projects. So today we have three different students that are going to be presenting to us their Masterclass final projects. Very interesting projects, but let's start with the first one, which is going to be related to the Starbucks cafeteria for creating an automated system for delivering coffees. So I'm going to introduce the first student in a moment. But before that, let me remind you that for all the audience who is here in YouTube, so you can share your questions for the student in the chat. And at the end, if we see any interesting question, we will add it to the Q&A session. So we are going to do a small Q&A session after each project presentation. So yeah, let your comments and thoughts here in the chat, and yeah, hope you get a lot of fun. But let's get started already with the first presentation. Who is going to be in charge of Regvith Baskaran? So hello, Regvith.
Hello, everyone.
Hello.
Yeah, hi.
Yeah, we can see you there. So yeah, it's all yours. You can introduce your project.
Yeah.
Okay. Yeah, we have your screen. We cannot hear you. I don't know if you are muted.
Yeah,
or...
yeah,
okay,
I'm
okay.
not muted.
Okay.
It's just that it's not going. Just a second. Okay. Yeah.
Okay, we are getting your screen. Yeah, there we go.
So I'm sorry about this.
Don't worry.
Project. So my project is about coffee cups placement using sensor fusion, and the table of contents it's divided into six halves. The first one is the introductions, and the second one talks about the image processing and path planning, and the third one is about web interfaces, and fourth one is about FPGA control logic, and the fifth one gives a complete flow of all the things. So let's start with the introduction. So the frameworks and tools that I've used for this are ROS2, PCL, OpenCV2, and other things that have been shown here. And these are the credits that I wish to give because I've used their models from Sketchfab and Mixamo. So this is a credit title. And let's get started with the introduction. So the coffee delivery process in automated environments requires seamless coordination between robots, computer vision, and user-friendly interfaces. This project introduces a web application designed to manage and monitor the entire coffee delivery pipeline. The objectives of this project is develop a web application to manage the coffee delivery pipeline, visualize the hole detection processes, the camera detection of the barista robot holds, enable robot control via command button to initiate delivery, and provide real-time monitoring and feedback. So the scope of automated robots is quite high. This is because there was a study by Lee and Hall in 2023 that showed that robot coffee showed more consistent quality, lowest food technology fears, and taste, and there was more stronger positive emotions for human beings. And right now, the global coffee shop market is projected at around 237.6 billion US dollars. And this was in 2020. So this facts has to be verified a bit more. And next, let's go on with the image processing and path planning. So I take the subscription of depth image, color image, and camera info, and then I process the inputs using the pinhole camera model, which generates this um, uh, point cloud map. So I take the depth map and convert it into pixels, and that gets further filtered. So after the generation of the point clouds, I use the cup detection is done using the published point clouds from the camera. So I do segmentation of the point cloud twice. So what this does is like it takes um, the surfaces and then it removes the surfaces and just gives the cluster of cups, and there were some noises also along with the cups. So and then after that segmented, I cluster the data, and then uh, the remaining points are clustered with Euclidean distance and clustered, and then they're made as centroids of the and these become the whole positions. And I transform these whole positions from the base link to the camera position, and that is done using a static TF, and that static TF gets uh, appended to the points that are being detected by the camera images. And these points are being published as visualization markers. And I'll show the image for that in this. This is the illustration of uh, the red balls are the detected holes or the clusters. And this is the top view and this is the side view. And this I also use a huff-based circle detection. So these are the parameters that were used for finding out the circles or holes using huff-based circle detection. But there was also this issue with the Starbots logo, and the circles started to get massively a lot of noises started being generated. So in order to reduce this noise, I started to use a cropped image, and that cropped image gave a more accurate positioning. And again, the depth was calculated using the UVZ formula that was used for the same formula that was used for finding the um, point cloud positions. And it's again transformed from the base link using the TF2 tools, and it publishes annotated images as well as the markers. So these are the annotated images, and these are the whole markers. And next one is the sensor fusion. The limitations of the using of point cloud segmentation was that there was a fifth cluster getting generated, and this is not ideal for as the cup will be placed at a wrong position. The huff circles perform bad with respect to changing lighting. So it started generating more holes when there was more lighting, and there was started generating lesser holes when the lighting was bad. So however, upon fusing both of them by subtracting their um, distance of the XYZ centroid values, the precision and accuracy of the cups getting detected get significantly improved. The yellow spheres are the markers of other markers, and the path planner. So the path planner is done using the kinematic path planning with OMPL, which uses the objects are placed to prevent it from collision. And these are fixed joint state locations because the robot starts to do a really weird trajectory that is not acceptable. So in order to avoid that kind of trajectories, a fixed path and a fixed position is necessary for placing the barista robot so that the cup does not topple over because of the robot arms kinematic trajectory. So, and this is next is the website interfaces. So the website was rendered using the 3JS and ROS 3D.js, MP JPEG library, and it is mostly developed using JavaScript. But there was an issue with the version that the ROS 3D library was using for the 3JS. It was using an extremely older version. So what happened was it started causing this a kind of ghosting kind of an image, as you can see in the first image above. So the second one is so to counter this, I had to use an overlay on top of the uh, along with the viewer that was generated, and the characters were taken from Vixamo. So and then the animations were done using the Blender platform. So after that, there was also this issue with the GPU. So after a certain instance, the environment was not able to be rendered because the GPU started to overload because of the images. So next is the FPGA control. So the FPGA design was basically done using RTL. So in this, I used the Verilog programming language, and I designed a new art controller, and the design uses a baud rate of 115,000. So that's 11500. So the logic is that there will be slides. The slide switches are, as you can see in the board, as soon as one is pushed, the slide switch corresponding to the corresponding room would indicate where the switch was pushed on, and it would also give a signal to the robot, the barista robot that would be navigating. Unfortunately, this project does not do navigation using the barista robot, but it gives an indication as to where the table is, and the robot would go to that position using the switch that gets pushed. But however, there was a problem with this approach. The problem was that the the UR transmission was only possible to the local machine, which is the personal computer, but it had to be transmitted all over the place so that it is accessible beyond the local computer. So for this, the MQTT protocol was used. And the MQTT protocol was written in Python, and I use a broker that is called as the Beehive queue. So the serial library parses the UR transmitted data from the FPGA board, and then creates a publisher to broker the data, and this data is subscribed to through the ROS checked, and the data that is then passed and then published as the ROS2 topic. This ROS2 topic is gets subscribed by the JavaScript and controls the state of order. If somebody wants the switch is pressed, UR transmits data. MQTT protocol then bridges the data. Holes are detected through sensor fusion. After the customer clicks the submit button, the service is called for getting the hole coordinates. The arm then places the cups to the holes based on the detected values. After the cups are placed, the robot will deliver to the tables. So in conclusion, the project successfully demonstrated a robot performing a pick and place operations where cups were picked up and placed into designated holes. While the system achieved its primary goals, improvements are necessary for it to become more robust. A major limitation lies in the reliance of static TF. Any slight camera miscalibration can cause the robot to drift from the whole location. Incorporating proper camera calibration has to address this issue and improve the accuracy. The full objective of this project could not be achieved due to resource limitations, including GPU constraints, occasional camera and robot downtimes, and time restrictions. Despite these challenges, the robot was able to perform really well within the available resource times, showing strong potential for further development. And with this, I'm done with my PPT presentation. So now I'd like to um, go to my this is my simulation, and this is the documentation for the simulation. So now I've run the move it to packages and the simulation for that, and okay, the robot did not start properly, so we'll have to restart the simulation again.
Okay, so Regvith, if you want to show us something here in the simulation, it's fine. Okay, but
Okay.
if it's not super necessary, we can go straight to the real robot if
Okay.
you want. Okay, so
Okay, sure. Because the simulation sometimes takes a while to like load, so sometimes it's
yeah, don't worry. So
yeah,
I'm sure everybody wants to see the real
real
robot
robot.
performing. Yeah.
Right. Yes, sure. So now I'll go here and I need to download the PCL library for that.
Okay, so we can see there
Hmm.
already the camera labs, the labs cameras. Okay, so what are you doing now? You are, I
I'm running
suppose,
the,
setting up some things, right?
yeah, correct. I'm setting up the ROS bridge, sorry, the Zeno bridge. And then now I'm launching the website.
Mm-hmm.
Um, and then after this, I do a calibration test before starting the test. This
Okay.
is because to check if the robot is like the holes are properly calibrated or not. But before that, I just wanted to change the ROS bridge address for this. And so, but I think I need to reset the state of the robot before that. And I'd like to show harvest demo of the full thing before.
And what does this calibration test do exactly?
So it just basically goes to one of the holes, and then without the cup inside,
Okay.
and then if it's properly in place, then the static TF is correct, or else we might have to update that. So that's the
Okay,
uh,
okay.
test. It's so it seems like the camera is down. I'm not sure what.
Okay, let's wait for a bit. Sometimes there is a bit of lag with that.
Hmm.
Or maybe what you can try is restarting Zeno also from your side.
Yeah, sure. Okay, it's down. Yep, there's nothing running.
Okay. Yeah, I have restarted Zeno, so everything seems to
Okay.
be fine there. So probably it's just a bit of lag. Okay,
Cool.
it should eventually come in.
Mhm.
Okay, do a roster topic list now. Somewhere else, just to test.
Yeah,
There it
outside.
goes. Okay.
Oops. Wait. So this is the demonstration of um, yep. So this is the point cloud topic, and this
Okay.
is the unnoted images. I just wanted to show it directly in RViz because the point cloud does not appear on my website. And I just wanted to show also the other cup holders that's there. And this is the point cloud based um, holes. And this is Huff based holes. And the values get fused after that. And now let's go to the website. So I use a game-based interface, like UI for control. So um, so this is the test I'm going to do. So I'm just going to run two values now, just to see, and
Okay.
the robot going to the home location. It goes to the home position first. Okay, it started doing the process. So yeah, it's starting. It started the process.
It's going for the coop, right? Right
Yeah,
now?
cup, yes. Yeah, correct.
Okay. Yeah, we can see it's leaving it there in the hole.
That's all. So I'm just doing two right now.
Okay. It's going to
And
continue?
yeah, it's going to continue.
So
But I wanted to
then
show,
maybe we can ask
yeah, so,
Rodrigo to put some more cups there.
yeah, sure. Yeah, sure.
Yeah.
Uh,
Yeah, go ahead, go ahead.
yeah. So it's going for the second hole. And I wanted to show like so this is the image, and
Awesome.
unfortunately the gripper was changed recently. So now, so the closing UI is not proper now. So there it is. It goes for the second hole. And that's it, yeah. So it's just two for now. They can replace back those two cups again. I just wanted to show it from first itself, if that's fine.
Okay. So
So this one, yeah, this is the I can. So this is basically the character that's here. Uh, okay, it's starting to lag a bit. Yeah, that's the character,
ah,
and I'm controlling him using so there's I'm controlling him using the keyboard. So W is for moving forward, and back is S is for moving back, and left, right. And so what I wanted to show now is like the reason why I wanted to restart this process was I wanted to show the FPGA right now. So FPGA based control. So
okay.
it would be great if you could change the position of the robot now to any other location maybe,
Okay.
and
And do you want us to remove the
yeah,
cups from the robot
yeah,
or?
yeah, that would be brilliant too. Yeah.
Okay, then let me ask Rodrigo to remove the cups from the
Yeah.
robot and then also rotate a little bit the robot so that we can see that the detections of the holes is actually live. So we can rotate the robot and the program should still work, right? I think the camera's freezed a little bit, maybe. It looks like. Are you there, Regvith? Yeah, it seems like we lost the screen sharing from Regvith. Ah, he's screen sharing again, but we cannot hear you, Regvith.
Yeah, sorry about that. I'm not sure why it randomly just logged me out.
Okay, okay. Yeah, we can hear you now back again.
Yeah. So this is the Python library, and sorry. So now I wanted to share my video.
Okay.
So now this is my FPJ. I'm not sure if it's visible.
Okay, wait 1 second because I don't know. I am seeing it here, but I'm not sure if the audience is seeing it. So let me verify
Yeah, it's this
that the
this
audience
image
can
here.
see you. If not, I will switch
Mm.
here my screen
Yeah, no.
for a moment. Okay,
Yeah,
yeah, so
sure.
let me do a
No
quick
problem.
switch to you because the audience
Okay.
cannot see it. Then, okay, now they can see you.
Okay, yeah. So this is the FPJ board.
Mm-hmm.
So now now I'm switching it on. So now you see it's switched on.
Mm-hmm.
But I also wanted to share the MQTT file. So now I started the publishing. So you can see it's publishing data from there. So now I go to my ROSjet, and what I do next is Python 3, and then ROS, SRC, and MQTT. And this, so as you can see, the data is being received from my house to the ROSjet.
Mm-hmm.
That's in Barcelona right now. And so the reason why I wanted to show that is, um, uh, yeah, that's okay. So now as soon as I press this button, the okay, it takes some time to render properly.
Mm-hmm.
So now it's rendered properly. Now, okay, it's lagging a bit.
Yeah, I mean, this looks like it's pretty resource consuming. So,
Yeah. So yeah, let's do it again. So yeah,
okay.
it's not rendering properly with this on. Just 1 second. It's better with Mozilla. So yeah, I think it's because the camera is also switched on. So that's one of the main reasons.
Okay. Okay. Okay.
So now do you see that this thing started to miss right now? This is because the goal of this project was as soon as this switch gets pressed on,
Wait, Regbith,
you
because
see,
I think they cannot see exactly what you are doing now. Can you put
okay,
there like your zoom camera
okay,
in the
yeah, sure,
so that we can
yeah,
they can see it because they cannot see your camera right now. So if you can bring it,
okay.
yeah, there you go.
So now the FPGA is in switched off state.
Mm-hmm.
So this is the second one. As soon as it's pressed, you see that the switch. You see the switch state change. It was 0 before, and the order menu also is here. So as soon as I press some name here, so I put Regvith Baskaran, and then I press the table number here, and you see there's like a um, order menu here. So if I put something like drip coffee and submit, now you see there's a text that gets generated because of all these details, and the robot starts doing the pose. I mean, it goes to the hole, as you can see here, and
Yeah, it's going to
and
grab.
then yeah, it's going to grab the cup now. It should have been a bit black, but it's okay. And yeah, it goes yeah to the next one. So there's it putting it in the hole, and yeah, one, and it's gonna do four more. So I think cup needs to be placed a bit.
Okay, so Rodrigo, if you can put another one, yeah, I see he's already doing it.
Yeah.
Okay, so I think we can maybe do one more and then
Mm. Yeah, sure.
leave it
Q&A
there.
after.
So
Yeah. It's a bit back, I guess. It needs to be a bit more.
say that again, Regvith?
And the cup was placed a bit backward. Okay, but it's
Oh,
fine. Yeah, that's
okay.
okay.
Yeah, it seems like it picked it still.
Yes, yeah, that's okay.
So there it's moving slow. So
Yeah.
maybe you can explain maybe why it's doing that.
So because it's out of the trajectory of the robots, you see it moves in small steps,
Mm-hmm.
but the robot has joints, like it has limits that
Mm-hmm.
it cannot reach after a certain point. So
Mm-hmm.
this steps is done using a fraction. So when the fraction is less than 0.9, that is what I've said,
Mm-hmm.
it wouldn't do a proper, like compared to the first two, it wouldn't go as good as that.
Mm-hmm.
It would just go like in a very slow motion like that, and then now it would because it cannot reach those properly, and this is the reason why it has to be constrained in order to do a proper
Mm-hmm.
motion in a particular region. So other than that, yeah, that this small steps is uh, ensures it to reach it, uh, even the destinations that would not be possible with a normal set set to goal pose.
Mm-hmm.
um, um, Sorry about that. The function that is used in movie 2 that is set to goalpost, it does not reach that if it's only reaching there because I've set it in Cartesian path planning, right?
Mm-hmm.
So that's what I'm saying. Yeah,
Yeah, yeah. So basically the robot is close to its joint limits and then
correct, correct.
it
Yes,
starts.
yeah. And there's also this clip over here that is making it a bit hard to reach certain places.
Mm-hmm.
But if you see now, all those four cups were easily
Mm-hmm.
compared to three, only one was because it was out of range. It was
Mm-hmm.
close to going out of range. And yeah, that's it. Yeah.
Okay. So yeah, if it's good with you, I think we can leave it here, Regvith. Yeah. So shall we go with the Q&A? Okay. So, all right. Yeah, I'm going to ask you, Regvith, also to disconnect from the lab, because next student is going to use the same lab. So if you can disconnect to the lab, that would be great. You are muted, by the way. We cannot hear you.
Oh, okay. I'm
Now
not sure.
we can hear you. Okay.
Yeah, I'm disconnected from the lab.
Okay. Okay. So yeah, then if you can share again your screen so that we can see you for the Q&A.
Yes, give me a second, just 1 second.
Okay, so yeah, then if anybody has questions for Regvith about his project, now it's the time to share them. So we have him here, and then I'm going to start with a couple myself, okay?
Yeah, sure.
Or at least one. So it's basically about this device that you showed now in the end. So from what I understand, oh, wait a second, because I need to pin you here. Okay, there you go. Now we can see you properly. Okay, yeah, so if I understood correctly, right, so the device, so what I'm interested in is how did you manage to connect the device to the project, right? Because the project is automatically connected, let's say, to the labs here in Barcelona, but the communication between your device and the project, if you mentioned this MQTT protocol, so
correct.
Is that one the responsible of bridging, let's say, the device with the project?
Yeah, that's true. That's correct. And so there's basically like a device broker. So it's the same way how Zeno works, like how I'm sending a client request to the server, and then the server responds to that. So similarly, what I'm doing right here is like I'm using Beehive HQ. So this is basically like a cloud platform that bridges like data from one particular location to another location. So this is what the beauty of IoT is. This is Internet of Things. So what happens is like if a device can be controlled anywhere if you just have internet. This is the best evidence that anybody can get. And I'm using a device that is completely in a completely different part of the world and I'm controlling another device which is in another place. So this was possible only through that Beehive broker, and I'm using this a protected SSL. So this means it's like security authorized only because of that, because we wouldn't want people overloading the object and causing some kind of crash or something if it's exposed. So this was one of the main reasons why I decided to make it make it through a secured platform. So the Beehive gave that opportunity. So yeah, that's how I am transmitting the data from here to there.
Okay. So Girish just shared a question, which I think is interesting also. He says, why did you specifically use an FPGA board? And then he says, can the same thing or something similar be done using Arduino or ESP32, for example?
Actually, ESP32 is the best compared to an FPGA. One of the main reasons why I'm using an FPGA, not like ESP32, is because there was no other device that had switches. This was the blunt and honest answer that I can give. So given the time constraint, I realized FPGA was overkill for this kind of a silly project, is what I would say. The reason why I'm saying this is like it's just transmitting one byte of data, but the FPGA is meant to be used for an extremely higher scale performance. So I feel like an ESP32, an Arduino, and any other microcontroller devices like PIC16F or STM32, they would do the job. They would get the job done too. And yeah, there is no need for a UART bridge it can be directly done using the ESP32, or even the Raspberry Pi can act as the broker for transmission of data. Yes.
Okay. So more questions. So for example, here Gish is asking also, what type of planner did you use for the trajectories of the arm?
So I was using the OMPL planner, so the default kinematic planner that and it started to use the RRT, that's the random tree that was being generated. So this was the planner that I used. Yes.
Okay, and how was your experience with it? You mentioned at some point that it was doing some strange trajectories. So
Correct.
how did you deal with that?
So that's the reason why I started to use a fixed position. I wanted to bound it to a particular position or location because as you could see when it went to that that the barista middle location, or as I like to call it,
Mm-hmm.
it was fixed. It was to a fixed position. If you put the robot a bit forward, I'm not sure it would be able to reach that position because I've programmed my code in such a manner that it needs to be in that particular position, because even though the path planner was reaching it, it started to topple the cup upside down, and it was not a good thing if something was held inside the cup or something like that, and then if something falls off, it's basically a project that was done badly. So I'd like to find a stable and a proper solution rather than a solution that's fancy. Yeah. So, yeah.
Okay,
So this was
so
the most stable, and yeah.
yeah, so if I understand correctly, then the initial part, so where,
Mhm.
for example, the first part where when you go to the cup
Mhm.
to grab it, all that
Yeah,
is based on fixed joint positions, right?
correct. Similar to that, yes.
Then you pick the cup and then you go
Mhm.
like on top of the
Mhm.
barista.
Yeah.
That is still using fixed joint positions, right?
No, actually, what I do is like I calculate the center, so I
Hmm.
accumulate all the points, and then what I do is like I've put a seeding for that. So
Hmm.
it's basically like it needs to find a particular position in between all these points so that it's reachable to all the positions that's there.
Hmm.
So how I've calculated was like using the average mean method,
Hmm.
and I publish that specific point x in XYZ
Hmm.
and the setup goalpost target, and then it goes to that particular middle location, and from there on it starts to go towards the other holes
Hmm.
using the Cartesian path planner, because this way it's a bit more optimized, but I
Hmm.
feel like it needs a bit more work to be more refined.
Okay, and okay, so I have one last one.
Yeah,
Then
sure.
in this line, because I remember from
Hmm.
previous iterations of your project that
Hmm.
I saw you and
Hmm.
was testing with you, that when you grabbed the cup and
Hmm.
then went to this ceiling, let's say on top of the
Hmm.
barista, right?
Yeah,
You
yeah.
were not keeping the cup uh,
Mm.
like straight, okay?
Correct. Yeah.
Then now in what you showed is that you are properly keeping the cup like this, right?
Correct.
Vertical, so that you don't spill coffee and so on. So
Hmm.
how are you dealing with this of making sure that the cup is always like this in a vertical position, so that for example you don't do like this or things like this with the
I'm
cup?
so sorry. Like, is there some kind of, I'm not sure if your camera is all visible, or are you showing something? I'm not
Ah, I was, yeah, I was, but maybe you cannot see it. The audience is
sure.
seeing it. I was just showing the
Okay.
cup. Yeah, but
Okay.
basically it's
Okay.
that. So now I have seen now in your demo that you are always keeping the cup.
Upstate. Yes. Upright. Correct.
Exactly.
Correct. Yes. So before it was not happening with the setup to goalpost, because it started doing trajectories that was like, it started going like this
Hmm.
and then going down like that. That's not a very good trajectory. Now imagine if some kind of coffee was actually inside that,
Hmm.
and if it starts doing this, it just spills a lot the
Hmm.
coffee that was ordered, and that becomes a waste of money, and especially and so that's the reason why I prefer a very stable solution, and it has to be done instead of a solution that's like, okay, I can go to any position. That's not the goal of this project. It's like the coffee has to be delivered in a single piece instead of,
Hmm.
split. So that's the main goal of it. Yeah. So that's the reason why I want it to be true to its nature. So yes.
Okay. All right, Regvith. So
Yeah. Thank you.
so yeah, thanks a lot. I think we
Mhm.
can leave it here.
Yes.
So
Yes.
yeah, congratulations for your presentation and
Thank you.
yeah. So we are going to be in touch in the following days.
Yeah. Sure.
Thank you.
Thank you.
Okay, so I see that we already have our next student here ready. So we are going to continue working on the same lab. with the same robot, but the project is different. So Regvith, one interesting thing that he mentioned during his presentation is that one of the project constraints that he has is the transform, right, between the camera and the robot arm. So he needs that that transform to be static, to not change, because if it changes, then his project breaks, which is understandable. So now we are going to go on another project that basically attacks this problem of how to properly get that transform between the camera and the arm. So I'm going to stop talking and I'm going to say hello to Hajar, who is already here. Hello, Hajar.
Hello, can you hear me?
Yes, we can hear you.
Okay, good. Yes, so today, as you have said, I will be presenting a project about the visual calibration of the camera that Regvith was talking about. So I can first start by sharing my screen. Can you just tell me if you can see it? I will be sharing this one here.
It's coming.
Okay.
There we go. Yeah, we can see it.
Okay, nice. So I will just start the diaporama. So yes, my project is going to be about visual camera calibration. So first thing first, we will just give an example. So for example, if I give you a mission, which is to grab a cup of coffee. So any person, if the person is away from the cup of coffee, he's going to go towards the cup of coffee and grab it. Or if he is immobile, sitting somewhere, it's just gonna go reach his arm and grab the coffee. I'm sorry, I will be just putting this here. Okay, so it consists of two main steps. We are going to localize the cup and then move our arm to grab it, which is quite easy for a human being. However, if I give the same mission to some kind of robot, then it's going to be a bit more difficult for it. Since the robot here, he doesn't know really where is the cup and how far it is. So if we do not give him a little more help, then it's not going to know where to go to grab it, and it's going to fail its mission. So this is actually our main challenge of if I have a camera which consists of the eyes of the robot and the robot arm. So even if the camera is separated from the body, which is the case in our lab, after I detect an object using the camera and have its position, how can the robot arm know this position in space so that it can go and grab the object? Okay, so to try to explain this a bit more, so we have the camera, it's going to make some kind of detection. It's going to talk to the robot and tell him that, you know, the cup is at XX far away from me. The robot is going to say, well, since I know my position with reference to the camera, I am YY far away from the camera, then maybe I can guess where the cup is. And then I'm just going there and grab it. And this is the main goal of this project. It's to try to establish a link between the camera here and the robot arm. So what do we exactly mean by a link between a camera and a robot? The link actually consists of computing the distance between the two of them, as well as the orientation, which means how the camera is orientated with reference to the robot. So we actually have some computer vision tools that are going to do that. So we can kind of, if I detect an object, I am kind of going to guess its pose. However, now we need to try and find out which object I really need to estimate. So if I try to localize the whole robot and estimate its pose, it's going to be a bit too complex since, well, we have the whole robot and it won't really fit inside the frame of the camera. So in that case, we will be needing something smaller with a reliable detection. And that's where the Aruco marker comes. So just to explain a bit about Aruko markers, they are simple patterns that consist, as we can see, of grids of black and white squares. They are small, and they are also used in augmented reality. So they have a robust detection, which is very interesting since we can actually, as we can see here, detect them from different angles. So even if they are orientated a bit differently, we can safely estimate their pose. And even in difficult lighting conditions, we can more likely safely guess their pose. So if I have the real size of a Naruko marker, I can estimate its pose. So here, to explain a bit more about the steps of this project, we will be taking a robot arm and then we will stick a Naruko marker on its gripper. And then the camera is going to try to detect the position of the Naruko marker. This will give us an estimate that is y. And since we already know the geometry of the robot, we can safely compute the distance between the base here and the gripper of the robot. So we are going to get z, and then we can finally establish the link between the base link and the camera link, which is x. We can deduce it from y and z. So next, I will be introducing the tools that we have been using in this project. So we are using the manipulator of Universal Robotics. We're using the UR3E version. We actually used two grippers in this lab. We used both the RG2 and the Robotic 85. As for the camera, it's the real SenseDepth camera, the 415. Well, for the software tools, we used ROS2. We used the MoveIt package for both the sensor communication and the robot movement. Well, for the computer vision tasks, we actually used OpenCV. As for the languages, it was mainly, the nodes were written mainly in C++. In computer vision, I used Python instead. Okay, so next we will be trying with the simulation before trying everything on the real robot. So the first step was actually preparing the environment. So here we are in a kind of barista environment. The robot is going to grab a cup of coffee from the coffee machine and charge it here on the barista bot, which is going to serve the customers later. So this step actually consists of adding all of the simulation world object inside the planning scene so that we can safely plan trajectories and not run inside the object of the environment, which is really necessary. So the second step is the Aruko detection. So what we need to do is to try and move the robot arm somewhere where it can be detected inside the camera frame. And then we are going to use computer vision tools to try to estimate the pose of the Aruko marker, which consists of both the position and orientation. And the last thing we're going to do is trying to publish it continuously inside the topic so that it could be used later by other nodes. So yes, the next step is trying to compute the TF, the transform, which is the relationship between the robot base and the camera. So what is exactly a transform? It's just a description of the relationship between the different frames of the different parts of our environment over time, since they may change over time when the robot is moving. For this purpose, we will be using a simple formula that consists of multiplying the transform from the robot base to the Aruko marker by the transform of the camera center to the detected Aruko marker. And then next thing, we will be going to broadcast the TF over time. The last step is actually trying to test the value that we will be getting if it's correct or not. So to do that, we will be using the same logic we have seen before. So I will be detecting some kind of object, which will be the circle patterns in the barista bot that we saw. I'm going to guess its position, and since the robot already knows how far away he is from the camera, is going to try to go towards that circle pattern. So the TF is correct if we can successfully go towards the detected circle. Well, in the simulation settings, everything went well and the TF was correct. So now that everything is working, we will be trying it on the real environment. So just as a reminder about the steps, in the real environment, we are going to do the same thing. So first I started preparing the environment, moving the arm. It was good. Everything was working nicely. The detection also went very smoothly. The estimation of the pose was going well. The third step, I actually computed the robot, the camera TF. It was going pretty well. However, when I tested the TF, it was not correct. So what might be causing this? Well, the first thing is that I actually was using only one Aruko detection in the simulated universe. So it was given, since the conditions were really perfect, it was given the perfect TF, the perfect correct TF. However, in the real world, we have noise and we have some poor conditions, which may lead to some wrong TF values. So my solution in that case was trying to move the Aruko marker and trying to sample a lot of different positions in space and calculate and compute the TFs corresponding to each position in space. So to move the marker, the first idea that I had is try to move the robot, sample positions where the marker is visible, and store all of these positions inside a file. So after storing them inside a file, I made a script so that the robot can go through all of these positions over time. And at each stop of the robot, I'm computing the TF during all of the trajectory. After that, I compile all of the TFs inside a text file, and then I compute their average and broadcast it. So I actually use the Move It tool to try and move the robot a bit to the right, center, and then a bit to the left, and going through all of these motions. However, I encountered some challenges, and notably when the robot was going a bit too fast. We can see here a demonstration of that case. So the robot is here. The estimated Aruko pose is here, which is accurate in this case. So the robot is going to move. And when it's moving, we can see that the TF has a bit of trouble to keep up with the long movement. So in that case, sudden movements are no good. So to try and remedy that, I tried to create a buffer and then compile all of the, I think that it was the 20 last poses inside the buffer, and try to smoothen all of those values to try to get some kind of average. However, it was not reliable enough. So after doing these tests, I tried to focus instead on smaller trajectories. So, and here I encountered another challenge. It was when the Aruko marker could not be detected. So we can see it also here in this video. So here the Aruko marker is being detected successfully. Oh, okay. Sorry about that. So here it's being detected successfully, and then when it's going to move for a bit, it's not detected anymore. However, I still get a TF that is wrong and cannot keep up with the robot movement. So what I did in that case was try to stop all of the TF computations that I was doing whenever there was no detection, and trying to compare the timestamps of the messages so that I can accurately compute the TF corresponding to the accurate Aruko pose. The third challenge actually was when I noticed that the starting pose of the robot had a really big influence on the values that I will be getting later. So as we can see here, I computed the TF with different poses, with different starting poses, and testing them really did not give the same TF value as we can see here. And one thing that I noticed was that I got the best readings when the Aruko marker was really centered around the camera frame. So this is what I went with for a starting position. The fourth challenge was when I was rotating the gripper. So what I actually was doing is that I wanted to sample the maximum number of Aruko estimates throughout all of the trajectory. So for each waypoint, I was going to stop, then rotate the gripper both in horizontal and vertical motion. However, when I was doing vertical rotations, I noticed that the Aruko detection was lagging behind, as we will be seeing here. So the robot stops and then it will be performing a vertical motion. The gripper here, it's performing a vertical motion, and then it's going to perform another one, and we can see that the Aruko has a bit of trouble to keep up. It's completely wrong here. So in that case, what I actually did is I noticed that I have better results without vertical rotations, so I just removed them. Okay, yes, the fifth challenge was something that did not have anything to do with Aruko detection, but rather with the circle detection. So just as a reminder, I was using OpenCV and I was using the half circle transform for the detection of the circles. But I was treating the video feed frame by frame and labeling each circle. And for each label, I get the position of the circle. What I noticed, however, is that the circle labels change over time, as we can see here. And at 1 second, I am seeing that this circle here is labeled C3, but right after that, it's going to be labeled as C2. So we do not have any reliable detections. Whenever I need to go towards C2, I do not know if I should label it as C2 or C3. So to remedy that, I used a tracker to track each circle over time. So I get the position of the circle, for example, C3, and then for the next frame, I will be trying to get all of the other positions of the detected circles, and I compare the distance between this circle and the detected circle in the previous frame. And if the distance is really guess that it's the same circle and keep the same label over time. So what I actually finally did, so just as a reminder, for my starting idea, I was going to make the user select the poses, the trajectory poses by hand, just give him the robot, he can go on the manual mode of the robot, move it in a lot of different places where the Aruko marker is visible, then record all of these joint values inside a file, and then we will be making the robot going through all of these waypoints. However, I noticed that it requires quite an amount of manual labor, as well as it fails if the trajectory covers a lot of distance. So instead, what we try to do is, since the goal is to automate as much as possible this calibration process, was to just make the user choose the first position of the robot where the Aruko marker is visible, and then we will be executing a safe small trajectory around that starting position. And at the end, I opted for a circular Cartesian trajectory, which makes the robot stay on the same plane. Actually, my last challenge, or my fifth challenge, was trying to adapt everything into the website. So I had nodes, I had code that was working, but I needed to start it after clicking on a certain button. So in order to do that, I needed to create services. I created a service so that the robot, upon precising a pose, the robot can directly go towards that pose, or after giving it certain joint values, it can directly go set up these joint values and go towards the necessary position. However, I had a bit of trouble with the trajectory and TF computations since I could not use the ROS2 actions. So in that case, because there was no support for the ROS2 actions in the ROSlib, excuse me, can you all hear me?
Yes, we can hear you.
Okay, nice. So yes, I could not use ROS2 actions. So instead, I opted for a communication via topics. I was sending start signals to the nodes, and then the nodes are always listening. So when I send the start signal, the node is listening, and then it thinks that, well, I need to start to do my job after receiving this message. And now we will go for the live demonstration to demonstrate all what I've been talking about. So to do that, I would just need to share both of my screens. So I will just stop sharing this one just real quick. And then I will share both of those. Okay, are my screens visible
Yes,
right now?
we have them.
Okay, good. So I need to connect to the robot, I think, first. Oh, I do not see the button to connect.
Refresh the.
Okay.
Yeah,
Okay.
you should have it.
Okay. Okay, nice. So we'll be connecting. So while we wait for the connection, I actually made some bash script since I have to start a lot of launch files. So instead, I opted for bash scripts to make the whole process smoother. So I have a bash script that will start the nodes for the web page. Okay, it's loading here. I'll be starting the terminal. So the real robot is using Zeno to publish the camera topics. So we will need to install it first. To do that, it's here. I'll be running this command. Okay. I have also already installed some of the Python libraries that I will be needing, especially OpenCV for the detection. Okay, so here it's taking a bit of time. So while waiting, we will just prepare our other bash scripts. Okay, so this one is for the web page. This one is for the robot movement. And the last one is for the camera calibration. I think that it's okay, it's all right. We'll be starting Zeno so that we can see our camera feed. Okay. So first, I will be starting the nodes for the web page, and after starting it, normally we should be able to see the web page here. Okay. So I will be starting the other nodes. Camera feed. And then the calibration. So whenever I connect here, I have made a 3D map viewer for viewing the robot model. Here it's taking a bit of time, so yeah. So the first step is actually, as we have said, that to move the robot towards the start position. For the start position, I have handpicked this position because it centers the Aruko marker around the robot. So as we can see here.
Can you put the cameras a bit bigger, Hajar?
Yes, of course, yes,
Yeah,
here.
so we can see the robot moving and yeah.
Okay, definitely. Yeah, it's here.
Okay.
Okay. Yeah. So yes, here we can see that the Aruko marker is being detected. So next we will be starting the trajectory for the detection, for the calibration. So when I click on the trajectory, then it's going to send via a topic a flag for both the trajectory node as well as the TF computation node, as we can see here. So what I'm actually trying to do is I can show you on the code editor. I'm going to create a text file, and I will be recording all of those values inside the text file. It seems that we lost the camera feed. Can you still hear me, Alberto?
Yes.
Okay,
Probably
okay,
just a lag. Yeah, there it goes.
Okay. Yeah. Then we can see that it's currently computing the TFs. So while waiting, and for the progress bar that we have seen here, I am actually publishing some kind of feedback, the progress for each waypoint via a topic, and I'm listening to it and adding it to the progress bar here. So we are almost halfway. For the website, for those interested, I used Bootstrap CSS files. They have some really nice themes, which are open source on their website. So we can also try to view the trajectory of the robot here. So as I have told you before, this is the Move It RViz viewer. So I have added the different objects to the planning scene, as we can see here. And this tool is really nice because it lets you perform a lot of trajectories. You can also try to set up the different joints of the robot. You can go to a lot of places. And this is exactly what I used when I was sampling the poses of the robot. So here we are almost done. Sometimes it just lags when the progress is at 80%. I hope it does not today.
At least we can see the robot there moving and rotating a little bit.
Okay.
So
Okay, because it was lagging at 80%. I did not really know why. But it seems okay right now. So for the frames here that we can see on the website, so this is the base link frame, and the one frame that we can see here is the one for the Aruko link. It's the same one here. It's almost the same one, actually. It's the one published by the robot. Okay, so we're almost done. So when we are almost done, we're going to shut down all of the calibration nodes and the trajectory node. So the next step is actually to try and test this computed TF. So when I click on this start TF broadcasting, I am going to compute the average of all the TFs that we have sampled right before. So here, so that we can visualize it. And well, I have another button that will start the circle detection. So here we can try to see the circles that are detected. And in order to go, so I have made buttons for the number of the circles detected. The buttons of the circles that are not detected are not enabled by default. And well, we are going to try with circle 3, even though I cannot see it well. Maybe I need to make the robot go towards the home position. I'll be just sending the robot towards the home position so that we can view it more safely. Okay, 0. And joints. And then we can see that we have the circle here, which is C3. Oh. Maybe we are just going to go towards C1
wait.
instead. Yes.
Give me a second. Probably it's because we have the cups from the previous
Exactly.
presentation. So let me
Yes.
remove them real quick.
Okay, okay.
Yeah.
Thank you. Okay, yes. Right now we can go to C7 in that case.
Okay, done. So we should be...
Yes. And well, as we can see that we have a bit of an offset on the Y coordinate. So I was not really able to resolve this issue yet, but I still can present some kind of solutions that I would like to try in the future. I will be going to the presentation since we've finished the live demo. Maybe I will just stop sharing. Oh, we can leave the 2 screens actually. So live demo finished. So for the conclusion. So our goal was trying to establish a link between the robot base and the camera, and to test this link by going towards a certain detected object, which were the circles of the robot. However, as we have seen right now, the TF still needs some improvements. So in that case, I was thinking about using a Kalman filter and keeping long trajectories to sample as many points as possible. Because from what I have seen, if the starting, as we have seen before, the starting position is really gives some really different values depending on where you place the robot. So I would like to still keep sampling as much points as possible. Also, the Kalman filter is really good since it can handle occlusions. So as we have seen before, when the Aruko marker is not detected, the filter can somehow predict its position pretty much accurately. And it can also use multiple measures in order to make this prediction. Well, I also thought about the use cases of this project in real life. So let's take, for example, if a person with no real technical knowledge about ROS2, about robotics and everything, if he ever broke the camera of his robot, then maybe he can use our solution, just connect to a website and do the calibration by himself without really needing some kind of technical advisor or anything. So I think that this could work really well in the industrial robots, as well as for the mobile robots. And on that case, I also wanted to introduce Mirokai, which is actually a small robot that works in hospitals. So it's kind of assists the nurses with their daily tasks. It can go fetch things. It can lift heavy objects. So the camera calibration is really necessary for this kind of tasks. Another use case this time is more about the tracking of the Aruko marker and objects, especially for the cobots or collaborative robots, which are robots that work along humans. So what we can actually do is stick some kind of Aruko marker on the target, and then the robot is going to track this target and adapt its behavior depending on the movement of both the target, of a mobile or immobile target. And so that concludes my presentation. Thank you all for your attention. And if you have any questions, please feel free to ask me.
Okay, thank you.
Yes.
Thank you,
Thank you so
Hajar.
much. Thank you.
All right.
I will be just activating my camera.
Yeah. So let's go to the Q&A screen. There we go. So yeah, now it's time for anyone who wants to share their...
Yeah, Alberto, it's just that I have a problem with I have not the necessary permission to start the video.
Wait a second.
Yes.
How can I do that? Let me see. What about now?
Yes,
Okay.
it's good.
Okay. So I think we can see you now. Not quite sure. No. Okay. That's my fault because I need to pin you here. There we go. Now we have you. Okay.
Okay. Okay. Nice.
All right. So so yeah, thanks for your presentation. Then let's go with some questions. So, for example, I have one question here from Girish, which is kind of, I think it goes in the line of what I wanted to ask also. So he's asking, what type of Kalman filter did you use? But I think you didn't apply the Kalman filter at the end, right? So
No, I did not apply the Kalman filter, actually. It was just a suggestion for the future works, actually.
Yeah, so my question then was in a bit in this line. So
yes,
we saw that the final result, the final TF that you are computing is it has a little bit of error, especially in the y-axis. So
exactly.
Your proposed solution is to use a Kalman filter, but what do you think that error is being produced in the first place?
I think that it's being produced by, as I have said, the starting position, because from the test that I have run, I have seen that different poses have pretty much accurate estimation of the TF along a certain axis. So we can have a pose that have accurate x-axis estimation, and then we have a pose where the y-axis is computed really well, and then we have another axis where the z is computed really well. So we need really to sample a lot of data from a lot of poses in order to get something really close to reality.
Okay, so basically, the main problem in this case would be the specific trajectory that you are running afterwards, that for whatever reason, because maybe it's lacking some specific areas, it's having a better weight, let's say, for good values for the X and Z estimates, right? But for the Y, it's lacking some more readings.
Exactly, definitely, yes.
Okay. And so Girish here is saying also, what do you think would be the best solution, assuming you have all the resources that you need? So I assume the best solution in case in order to solve this specific problem of improving the accuracy of the TF, I suppose.
So sorry, could you repeat that?
Yeah. So what do you think would be the best solution, assuming you have all the resources that you need? So I understand. So probably the solution that you would think best for this specific problem, which would be in this case, from what I understood, the Kalman filter, right?
Exactly, and try to go through long trajectories and sample some really sample as much positions as possible. Place the Aruko marker everywhere inside the camera frame.
Okay, yeah, so then my question would be, from everything that you've presented, challenges and everything, so what has been the hardest part for you about this project?
Well, the hardest part was actually trying to get some really accurate TF, and I was really baffled when everything was working really well in the simulated scenario, and then you go towards the real scenario, you have nothing is working well, and then you have to really try and find exactly what's going on, why is this not why is this not working well, emitting some hypotheses, then you need to verify them, which is actually quite challenging, but also very rewarding.
Okay, so we have another question here from Desire, which is
Yes.
also interesting.
Yes.
He says, what happens to your offset? I would say to your solution in general. So what happens to your solution if you improve the lighting conditions or reduce motion blur? So for example, how is your solution affected by lighting conditions?
Well, actually, not much, since, well, it was actually affected first because we had some very difficult lighting conditions. So the Aruco marker was really not detected in a lot of places. And when it was not detected or was not detected accurately, it also generated some fake computations, as we have seen before. So it actually mattered in the offset. I had a bigger offset actually without good lighting conditions. But however, when you added the lighting as we did some weeks ago, it was a lot better. I noted that it was a lot better since I was getting some real good detections.
Yeah, yeah. So yeah, we did some changes in the lighting condition,
Yes.
obviously, in order to try to improve a little bit the detections. It worked. So
Yes.
so yeah, in general, even though Aruco markers are good, right? So are not affected heavily from lighting conditions. Still, obviously, you need to use camera. You need to detect things through a camera. So there's always going to be a certain level of importance from the light conditions. Yeah.
Definitely. Yes.
Okay. All right, Hajar. So I think we can leave it here. So
Okay.
So yeah, thanks a lot for your presentation.
Thank you so much.
Yeah, so we will be talking in the following days.
Okay. Thank you so much. Goodbye.
Bye bye. All right. So yeah, then we have one last presentation remaining, which is going to be totally different from the previous ones. So let me see if we can have the last student join us here for his presentation. Yes, so he should be joining us soon. Then, okay, so yeah, the last student is Robert. He is going to be coming here in a moment, and he is going to actually present us his project, which is related to humanoid robots. Okay, so we are completely switching the topic from robot arms, cameras, vision to working with humanoid robots, which is going to be a very interesting topic. I think that from what I have heard, that he even has a small humanoid robot, a real robot, I mean, right? So we are going to be able to probably see that robot a little bit if he allows us to do so. So yeah, his project is about ROSifying a humanoid robot. Okay, so both in terms of simulation, real robot, humanoid robots are really complex robots, right? So many things that need to be taken into account when working with humanoids, right? So yeah, hopefully with Robert's project we can learn a little bit about this complex but really interesting world, right? So let me see. He's not yet here, so let's see. He should be joining in a moment. Okay. Ah, okay. Okay. Ah, there you are. Yeah. So can you talk, Robert?
Yes, it's okay. Can you hear me?
Yes.
Great. Thank you. I am out of YouTube now, so that I'm not so sure I'm going to be correct or not.
This is because I saw your username is owner for some reason. It's not Robert or whatever, so I was confused. But yeah.
Oh, I don't know why it would be so, but yeah, I did. Did. Thank
Okay.
you.
Okay. Yeah. So let me wait a second. Let me switch the screen so that everybody can see you. So here we have Robert with us, and yeah. So without further ado, it's all yours. You can get started.
Thank you. Okay. Hello, everybody. Thanks for staying for my presentation. So I'm going to share my slide first, and maybe try to switch back because I cannot see my.
I can give you feedback if you need it, Robert.
Okay, I think I will turn off my camera and share my
Okay.
PowerPoint. Thank you. Turn that off. Seems that once I try to make it into a slideshow, I cannot share. Okay, anyway.
Okay, your screen is being shared now, and we can see your screen. Yeah.
Great. So thank you. Thanks again. My topic today is like I would like to take you to my journey to the world of humanoid robot that I have been going through this summer. My name is Robert Kwan, not Robot Kwan. Okay. So before I start my presentation, my little robot would like to welcome you first. Thank you for joining to this presentation. It's that.
Okay, really cool.
So to make it a light and easy to understand presentation, I'm going to use a 4W and 1H approach to present this project. So first, what is a robotics premium robot? This is actually a DIY robot kit manufactured by the Korean maker Robotis, mainly for STEM education or some hobbyist projects. It has allowed 29 different types of robots configurations to be built from that DIY kit. They actually provide very good window-based PC software tools for their development. For their hardware, they used the ST Micro CM530 microcontroller, and they also use the Dynamiso servers with the model AX12A motors. So this is a diagram that I captured from one of their websites, which show that some of their configurations of the kit, which they can be transformed into a spider, a dinosaur. And in this project, which I did is I tried to make it into a humanoid shape. And I did the type A, which is supposed to have a 18 degree of freedoms, which is like a very popular research topic before using this model, as far as I know. So here's a summary of which type that I said that afterwards, which, so like you see that this is the 18 degrees of freedoms, mainly 6 for the arms, for the both left and right, and then for the left and right legs, there's another 12 degrees of freedom with the hips, the knee, and the ankle. And here's another RQT graph that showed all the link and the joint connections for this robot configuration. So when did this journey started? Now I to call it Type A because it's a Type A humanoid in the configuration. The Robotics Premium first released as a product back in 2009, even before the ROS one released in 2010, sorry. And I myself, I purchased this kit in early 2020 during the pandemics. And then I assembled it and got the basic control working, but I didn't know anything about ROS at that time. And then I put it aside. So for this project, I discussed with my tutor, Ricardo, and got his support. So he suggested me maybe I should consider to try to ROSify this robot. And that's how I began my journey. So why did I have to do this? Because first I thought that you will learn some other projects from the class, from the master class, but not covering the humanoid robot yet. So that would be good to explore. And then I already had the real robot hardware assembled for use, which I just put aside without touching it for years. And also, it's just a good learning process for me to learn how to use the roster control onto my humanoid robot. So what are the challenges that I encounter during this ROSification process? Number one, the hardware was more like a closed system before. As I mentioned before, they did very good job. They provide a lot of good Windows-based software, but they didn't provide a lot of support to the ROS-based solution because they started the project even before that. And even though I could find some online from open sources, some people posted online, but most of them were not well maintained anymore. And it's not easy for me to replicate even with the ROS one based resources. So in order to make it workable with the ROS2 scenario, I decided to use the Raspberry Pi 5. And then I bought another U2D2 communication module from Robotics that will allow the connection for control to the Dynamiso servos through the connection like this diagram to bypass the control of the CM550 530 microcontroller. So here is what this U2D2 look like. In my configuration for that Dynamiso servo, I had to use the baud rate 1 million but it doesn't, the communication itself, it doesn't supply any power to those motors. So I actually need another power supply to those 18 Dynamiso servos, which support the 18 degrees of freedoms I mentioned earlier. And so after I applied that, I had to check. So this is like how I checked, like I wrote a very simple Python script. And then you see that I connected on the right-hand side, there's a DXL port in the middle that would connect back to the U2D2 module with the red light on. And then you can see that I can see that like the detection of all those 18 servos successful here. Then the challenge number 2 is the roster migration. After discussion with Ricardo, he suggested me to look into ROS2, Jesse, and Ubuntu 24.04, which is supposed to be a more stable, mature, and the latest environment to work on. So that's how I came to this on my Raspberry Pi 5. As I mentioned earlier, like all the resources I could find online from GitHub or some other places. They're mainly for the older ROS1 platforms. And I tried some of them and they were not well maintained after several years. And so some of them I had difficulties to replicate again. And then for those newer ROS2 resources, they support the newer communication protocol, DXL protocol 2.0, instead of the older 1.0, which I needed to work with the older Dynamiso AX12A motors, which are being used in this Type A robot. So as a result, I had to try to modify some of the driver codes to support the backed the older protocol, but on the ROS2 platform. And so this here is just a very high level system diagram on what it would involve in my project. So like I got first on the left-hand side, upper side, you see the robot description. They had originally a URDF that I had to clean up and modify to make sure that it would work. And then I got the roster controller and then the hardware interface that would support the DXL protocol 1.0 to communicate with my robot hardware. And then the roster control will also have the robot state publisher working and sending the data topic, whatever, back to the RIS2 or my simulator. And then another topic during the ROS2 migration, I noticed is that because once the ROS2 control node is launched, it would take over the USB port access completely. And so I would have no way to update any other motor register parameters, such as like moving speed for different motions. So for that, I modified some of the code so that I could send using services to read back and to update those parameters in the motor registers. So here is a screenshot showing that very small. Sorry for the small, but you see that I have at the bottom on the right hand side, it shows the services of get the DXL data or set the DXL data through the Dynamiso hardware interface. And then, so this is up to the point that I got the URDF working. And so it can be displayed in the RIS2 and also having the GUI that can control the different robot drones. But then it came to another new issue. Like you can see from here, the new issue here is that there's some joints misalignment. So even though it was working, but you see that the arm are twisting into the opposite direction, which is not my original intention. They're supposed to be going into the same direction. But it turned out that this is not the case. And here is the simulator that the gazebo sim, which will show the same issue. So I started to look into more about the motor itself to learn about how it would behave like that. And then I noticed that I learned that like from their tool and then their spec that for the AX12A, they have many different registers that you can work around to control. And the main one that I needed to pay attention is how the goal position is actually to be defined and to control. So you see that on the right-hand side is a picture from their user guide that the center point is like, it says 150 degree, but you can turn clockwise and counterclockwise. So based on that, I needed to do some manipulation on whether I want to twist clockwise and counterclockwise for manipulating different John's directions correctly. And so along that, they actually have a very good motion control format file called .mtn to give different motions. So this is a very simple format of their file. And you can see that the second line is a version 1.00. That is what I mentioned about the DXL protocol 1.00. And then there's a key one. And then some of the compliance and play parameters, those are for the different registers in their motors. And then the steps is the keys to what I mentioned about the values of those goal position that they're trying to target to. And so I had to interpret actually carefully and correctly on how the motor should be controlled, because all these values, they are only based directly onto the value putting inside to the motor registers. But in ROS2, I had to interpret them back to the correct radians or degrees to control correctly. So my next line here is I show how I interpret those motor goal position values back to the radians and the degrees based on their direction, so that you can see some positives, some negatives there, and then to control the robot correctly. Then after I got that done, I started to look into the gazebo simulation. At first, I tried to look into the Gazebo Classic, which we also use mostly in our class, in our master class. And I actually changed the modeling to my own modeling already. So it looks fancier. And I can show you that how it was like before in this video. You can see that it is shaky, but it will still move forward. Okay. But the problem is I cannot really use this older Gazebo Classic simulator onto my platform, because Gazebo Classic is not no longer supported into the newer roster Jesse and the Ubuntu 24.04. And so I needed to try some of the newer version of the Gazebo Sim, which is the Gazebo Sim harmonic version. And at first, I had difficulty to really set it up to control through the Gazebo Sim. And then Garish, our another tutor, helped me to look into the command post topic approach. So I started to implement that, and then I got it working, fortunately, like this. But with the Gazebo Sim, I encountered another new issue. That is the gravity issue. You can see in this video, unlike the Gazebo Classic, which could move without falling down, even though it was shaky. But in the case of Gazebo Sim, this is not the case. I tried to play around all the different physics engines available in Gazebo Sim and try to play around different parameters inside, but I could hardly find a good one. And this one is based on the normal 9.81 value for the gravity. I try to play around different, like for example, make it almost like zero gravity, but then you will see another adverse effect by tuning that around. You see that it's going to float up into the sky. So, because that didn't work, I thought that I would like to try some other approach. And then, with the help of Alberto, I looked into the CC roster control again, which I actually looked before, but it didn't work for me, so I gave up. But with the more information from Alberto, I looked into that again, and fortunately, I finally got it working in the sense of it would work, but I still had the same gravity issues. So these are the control config that I set for that gazebo sim. So you can see that actually this is the same, that there would be no difference on the behavior to the gravity is the same. So, and then I talked to my tutor, Ricardo. He recommended me to check the inertial block model. And so I found out, oh, this is really a mess. It doesn't look good. This is like this at the beginning. And he suggested me that it should be more closer to the shape of the humanoid robot, just like the collision model that I already have like that. So I spent some time to make it up to this point. But unfortunately, even though after I fixed the initial model to more look like the resemble to the humanoid shape, it still didn't work. Therefore, it came to me with another suggestion from Girish, that is to try Muzoko simulator. And so I started to look into it. Muzoko was a small company before they focused on this simulation later, but they got acquired by Google DeepMind, and it seems very powerful. And it looks very nice and very sophisticated. But the problem I encountered with it at the beginning is mainly the conversion from the URDF file to the XML file format for the modeling. I couldn't find any good conversion tool, and so I had to do a lot of manual check to try and error to configure how the XML format should be, and got to this point finally. And fortunately, it does give a very, very good result with this Muzoko simulator. As you can see from this video, it can now walk. I mean, this is not walk, actually. This is an attack motion, but it will not fall down. So now I would like to try to give a real demo. Let me try to set up. I need to switch my access because I need to take another camera shot of my robot.
Okay.
So I will stop sharing from here.
Okay. So you are going to use the second camera, Robert? You are muted. In the second one, we cannot hear you. I can see there the mute icon in the new camera. Yeah, we can't hear you yet. So I can see you now here, but I cannot hear you. Let me pin this camera that you are. Yeah, so we cannot hear you, Robert, still. Let me send you a message. Robert, can you hear me? Hello, Robert. Hello, hello. I think you are not.
Yes, I can hear you. I can
Okay.
hear you. Sorry.
Okay, okay.
I can hear you, but I think that's the two separate. So you see here is my real robot,
Okay.
and behind is my Raspberry Pi setup there. I already set up the reads, everything. And this is where I put my Raspberry Pi 5 holding by the battery we had for the fastboard. And this is the U2D2 communication module connecting from the Pi 5 and then back to the robot. Here I mentioned earlier. So now I'm going to show you backward moving because you see my desk is a tiny desk.
Yeah.
So I don't want it to fall onto the ground. So it would take some time at the beginning because what it is doing is that it is trying to configure those parameters inside the motion files as I just showed earlier in the slides. And there's 18 such settings. And now you see it's clicking to the walk ready steps. And this is very slow motion. And you see that this is actually shifting the focus between left and right leg and then to get it moving.
Yeah.
This is very slow because I haven't mentioned that even though there are parameters to control, but there's also some proprietary parameters which I haven't got any updates back from Robotis. I tried to contact the Robotics USA support, and the guy was very nice to reply me that he said he would contact the back-end developer to update me, but so far I haven't got any update.
Okay, and this is so this right now is working with ROS2 control and everything, or here are you sending velocities directly to the motors?
Yes, correct. This is using all ROS2 control.
Okay.
And you can see that the wrist can also follow the movement. Okay. So it would take quite some long time to finish all the steps behind. So I will move back to the presentation again. Thank you. Oops. Okay. Okay, so I left there. So let me go back to this here. Sorry, hello. I'm sharing. Can you still see my slide sharing?
Yes, we can see the slide right now.
So actually, just in case that I couldn't get the real robot up and running, I actually prepare another opposite video, which is showing the forward movement. The one that I show you is just like walking backward. But just in case that it didn't work, I prepare another one walking forward in this video. Again, as I said, that at the beginning is going to upload all the motor parameters, each of them, 18 of them to it. So that's why I
see the video.
Oh, you cannot see the video?
No.
Can you see the slide? You cannot see the slide, the screen.
Yeah, I see the slide, but
the
it's
slide
like
doesn't
empty.
have the video.
It's like empty. I don't know why, but
why that empty seven? Let me stop sharing and reshare again.
Yeah.
That would help.
Yeah, let's try that. Okay, now, yes.
Now, yes? Okay, good.
Yeah.
So, yeah, this is already walking forward. No. Seems very slow. I think suddenly it stopped. So you can see that the robot is actually like really moving forward very slowly and with small steps. So I think I better stop here as I have still some more to show you. Okay, so in summary, to summarize, I was lucky to successfully apply the roster control to the Robotics Premium Type A robot with ROS to Jersey and Ubuntu 24.04 on my Raspberry Pi 5, and with the use of the U2D2 USB communication module to the Dynamiso servos. The motion files can be processed and configure the motor's parameters as well. I can run both Gazebo Sim and Muzoko Simulator, but Muzoko Simulator does perform much better in terms of the gravity issue. And I put all the works into my GitHub repo for sharing. And I think that the more I learn, the more I know that I don't know. And what I went through is just a very tiny and primitive part in the robot world. And this diagram that I got is actually from Google DeepMind Git repo. They listed all these different models that they already have for the Muzoko simulator. And you can see that they don't cover my old Robotics Premium inside. They have the OP3, they have maybe the Darwin and some other models. And now I would like to talk about the limitations. There's actually a lot of limitations that I haven't mentioned earlier. Like, for example, originally I had another wireless control, but that would only work with the CM530. But now, because I have to try to get everything under ROS2 with the U2D2, and that's why you see all the wiring connection. And the utility tool is actually having some issue to drive all the 18 motors. I mean, it doesn't give the power itself, but I think that's still a little bit overloading. Plus, of course, my Raspberry Pi 5 is also a very low-cost computer at the same time. So all this combined together, sometimes I didn't show you on the screen, but sometimes the access to one or two motors in the middle would fail, but fortunately, it will still continue to the rest of the motors. But ideally, I should have a much more powerful platform in the future to run all this again, so that things would be hopefully smoother and faster. And then, as I mentioned before, the gazebo seemed really caused me a lot of trouble because I tried to play around different physics engines they had, Dart Sim, TPE, Bullet, but none of them really worked for me. And the robot actually came along also battery, but I didn't use it in this experiment here because the battery, even after I fully charge, it would only last 15 to 20 minutes for the operation. So it's very inconvenient. That's why I just plug into the power directly. And as I mentioned again, too, there are some proprietary parameter for robot control, which I don't have access. Now I will explain why I see that you see the motion for the walking is so much slower than the actual one that I could have achieved with the CM530. And also there are some other sensor which came along with the original DIY kit, like the IMU and the distance sensor, but I didn't take the risk to disassemble my robot to take out the wiring to be routed to my Raspberry Pi 5 this time, which I plan to maybe just to get another newer IMU sensor or distance sensor to route directly to my Raspberry Pi 5 in the future. So the end of one journey is the beginning of another journey. So here's some future works that I would really like to continue if I have time and resources. So first one is like the humanoid navigation, but I cannot find any good low-cost mini LiDAR that can help me to replace the current dummy head into a LiDAR sensing head yet. You see the price here, 1,200 something US dollars, which is about the cost of my tiny robot already. And as I mentioned before, that the IMU data, that I hope that it can improve the body balance and stability control if I have it. As I also mentioned before, that Robotics, they do provide very good tool on the window-based. So here is one of their latest window-based software that seems to allow people to play around, control the motion sequence with their editors. And so I would love to get that also into Linux-based later. And here are some works that I actually did before, but I didn't include here. Like here, I can actually voice control. Hi, Yabun. Go ahead. So you can see that this one is walking much faster because this one is based on the motion control from the CM530 directly. But I just added the voice control module and then I sent back the recognition result back to the CM530. And then I also tried object detection, and I actually got it working on my Pi 02 module, but unfortunately they don't support a Ubuntu platform. And I originally wanted to try the AI camera, which is one of their newest camera module with the sensor module from Sony. But unfortunately, I couldn't get it working on either the Pi 02 nor the my Pi 5. So I actually returned that module. So finally, I would like to thank all the supports that I received from Ricardo, Alberto, Grisha this year for all their invaluable guidance and continuing supports to help me to finish this project. And also, I would like to thank all the related open source contributors that like Robotis and Yaboom, their supports for me to be able to learn up to this point. So to thank them, I prepared another video. Thank you.
Okay.
So now it's this time for Q&A, I guess.
Let's give you an applause there. All right. So thanks a lot, Robert, for the presentation. So yeah, let's go with a bit of Q&A. So as always, let me remind everyone to share their questions for Robert here at the chat. I myself has many questions, so let me start myself with a couple. Girish says, you answered all my questions, Robert. No question for me. Wonderful research and presentation. Okay, so yeah, well done. Let me switch here to the Q&A screen so that we can see you there. Give me a second. There we go.
Let me
There we
try
have
to
you.
log back to the YouTube too. I cannot see any.
Okay. Well, here we already can see you. So yeah, I have many questions. Then okay. So for example, all right. Let me try to think of some quick questions so that I don't take all the time. But basically, so for example, one that I am interested is we saw that using that without using ROS, right? So you were able to I am hearing like myself. Probably because you have YouTube there opened, right? So if you can mute it or something.
Yeah, I muted already.
Okay. Yeah, so we saw a huge difference in the movement of the robot when you were using ROS and when you were using directly the motors, right? For example, in moving forward and so on.
Yes.
So
correct.
How could we improve the movement speed, for example, for when the robot is walking, still continue using ROS?
First, as I mentioned that, like I tried to contact the robotics company to ask for their technical support to see if they are willing to disclose some of their proprietary directories, proprietary parameter, because from their tool, I noticed that they have one parameter called control inertia parameter, and there's values there inside. At the beginning, I tried to apply that parameter value directly to their torque limit control parameter register. But I find that if I apply that parameter directly to the torque control register, it will slow down to even much slower than what I showed you earlier with the robot. So I know that it couldn't be direct control applied to that parameter. So I sent email to ask them, their technical support. I asked, oh, is this correct that my understanding that whatever you have in your PC2, they may not be directly mapping to direct control to those register values. There's some high level proprietary hidden manipulation inside their PC2s before they send to the register. And the answer I got back is yes, they do have that. But because the interface that I had is from more the customer support, he doesn't know the details of the technicals. So he said he would forward my question back to the developers. to see if they can answer me. And so I've been waiting for their update for a week, but I haven't got any update. But I can wonder because now, to me, that is the main parameter that is unknown to me. For all the parameters, I already learned how to control that. There's another parameter called moving speed that in the one of the slides I show you that one like the play parameters, there's one parameter that's actually to control the moving speed times how many times the original value inside the moving speed register. So I think that I may be able to try to play around with that to try to see if I can increase that moving speed for some of these walking movements. In fact, you see that for the hard motion and for the bowing motion at the very beginning, those are actually same as the one that in the original CM530 control. You don't see that kind of slowness. That means for those simple motions, I think probably also because not involving the leg movements. So that's why they could be up to the same speed control. And for the last, the heart movement, actually I decide myself, I prepare particularly for this presentation. I capture the values through a Python script, and then I created my own motion file, and then I try it out into my robot because they don't have that kind of motion. But the bowing and the walking movement, that's very standard movements that they already provided those files before.
Okay, so it's definitely possible, right? To improve
Yes,
it,
I think
even without having to improve the hardware or anything.
Yes.
Okay.
Okay.
Okay, so we have several questions here. Okay. For example, we have a couple from Desire, from Takabarasha.
I did try the damping. I tried the friction.
You are, yeah, so one second, Robert, because you are reading the question, but probably, so yeah, the first one it says, if you introduce some form of damping to the joints, do you think that would eliminate the falling problem? Yeah. That is the question you were answering, right? Yeah.
Yes, unfortunately, I tried that with different values already. I added into the URDF, and I couldn't find any value that would actually cause any difference. Yeah, so it didn't really help.
And okay, so from what I understood also, so you kind of have to design the hardware interfaces, right? To connect ROS2 with the drivers, right? So
Uh-huh.
yeah, you kind of had to create by modifying some code and stuff the hardware interfaces, right? To connect.
Actually, not much. Actually, not much. Once I bought that U2D2 communication module from Robotics, things became much easier because that U2D2 is supposed to support those their dynamical motors function. But the problem with that is that the robot itself has 18 motors to be controlled. And so there, as I mentioned, that there's still some limitation and stability for one U2D2 to control 18 motors at the same time. That's why you also see the slowness there too. I think that's another contributing factor. Because
Okay.
yeah, I looked into some online resources. They did mention they would suggest maybe you should buy two U2D2 modules so that you split up those motor control into two different sets. So each one has to only control 9 motor. Then that would make it faster and easier. But then that would add more work from my side because I may have to see how to coordinate that two different sets of controls.
Okay, so from the ROS side, then what type of messages are you sending? to the motors?
From the ROS side, like now I'm using the ROS to control, setting the follow trajectory parameter. That is mainly just for the position control.
Okay.
So the position control, that in the ROS2, there's I think defined as in a radians, right? So that's why I mentioned in the register the rotor, the motors they accept into their hard-coded values, which I had to do another conversion formula to convert from the radians back to the values that the motor register can read.
Okay. I understand. Okay. Yeah, the site is asking what communication protocol the UTD2 uses. Is it serial or?
It's just a serial, basically. Yeah, it's a serial, but if they have their own format, they have their own format called DXL protocol 1.0, which is actually just 5 bytes that with some header information, but it is actually just serial, just like UART, but into their own formats. Nothing really that magic.
Okay, Robert. So I think we can leave it here. Yes. So
I have one last slide to
yeah,
show that
go ahead.
before finish. Can I share my again? I go. We can finish, right? There's the last one. I have one very last video to show.
Yeah,
Thank
well,
you.
I want to say, meanwhile you prepare that final slide. I want to say that it's a pity that you didn't prepare the dinosaur robot, because then you would have had my 10 directly without questions or anything. If you did the dinosaur configuration for the robot instead of the humanoid. Just a joke, just a bad joke.
I would like to say the opposite. I would like to, it's so early here for me, my time. I would like to have a cup of coffee after after watching the first 2 previous presentation about coffee. Here, let me see if I can share my screen again. Session that is stopped.
Let's see.
Can you see?
No.
Can you see
Okay,
my
now it's just
sharing?
starting. Now it's just starting. Yeah. Now we can see.
Good. So yeah, my very, very last video that I prepared another motion to thank everyone who attended this. Oops, I don't see it.
It disappeared now.
Is it here?
Yeah.
Screen share as the share window is closed. Share window is closed. I don't know why. Is that? Can you see it now?
Yes. Now we can see it again. Yeah.
Okay, so yeah, thanks for attending my presentation. And so now this is my final video, really final. Adios.
Adios. Okay. Really cool. Really cool.
You. So I will stop sharing them.
Okay. All right. Thanks a lot, Robert, one more time for the presentation. So yeah, let's then finish it here. Thanks everybody for all the students, of course, for preparing their presentations. I know that it's been a lot of work from their side, a lot of effort, but yeah, they have all delivered very, very good presentations. So congratulations to the students. Also, thanks to everybody here watching the presentations. I hope that you enjoyed them, that you have learned something new from them. And yeah, so let's leave it here, and we will see you again for the next students' presentations. So stay tuned, and yeah, as always, keep pushing your robotics learning. Bye bye.